This is a presentation of three members, and the topic we are discussing is Z source inverter. So we have our power converters. So we have a conversion from AC to DC or DC to DC, depending on what we want. And the operating switches that we are going to be using can either be diode, IGBT, or MOSFET, depending on what is available to be used at the present moment and what we prefer to use. So we have a single or three-phase inverter circuit. The single phase has 4 switches and the three phase has 6 different switches. So this is the operating circuit of our power. So we have the usage of all of our power converters. It can be used for varieties of usage, but we picked out the main and the most important usage, which is it can be used as high voltage DC transmissions, it can be used as chargers, and it can be used as variable frequency drives. The basic composition of our circuit is that the V source it has a voltage source and a large capacitor coupled with it. I source converter. The circuit diagram is the current source and an inductor, and it has 6 switches. But the basic difference between the V source and the I source is that it works in a vice versa operation. When we have a buck converter in AC, we are going to be having a boost in DC using the same concept. That is the major difference between the both. But the mode of operation is almost the same depending on our desired outcome, whether we want a buck or a. So we have a limitation of that affect our AC, that affect our V and I source. First is that the DC to DC boost converter is needed. If we need a very large output, we will need the DC to DC boost converter, and this of course makes our whole project more expensive, because if we have to be buying DC to DC boost converter, it makes it expensive. So we have the possibility of shoot through in V source, and this possibility is if a leg is open, when the upper part and the lower part is open at the same time. But we can solve this problem with dead time, but this dead time of course gives us another problem, which is the wave distortion. And we have a possibility of open circuits in I source, which is if the total part of the upper layer is open and the total part of the lower part is closed. We can also solve this problem by overlap time, and this also gives us the problem of wave distortion. Both V and I source are vulnerable to EMI noise, which can trigger the gate to be on even if that is not what we want. And if gate is on at an undesired time, we can either have a shoot through or a open circuit, which is not our desired outcome.
Okay, so then we come out with a revolution, as has been done, the Z source converter, to solve the limitations we know. The Z source converter is just like the normal converter, except that it is coupled to what we call a unique impedance network. And this impedance network employs the use of 2 capacitors and 2 inductors arranged in this form. It can do AC to DC or DC to AC, AC to AC, and DC to DC conversions. They can be either back or boost, depending on what we want, unlike the I and the V, which is one at a time, but this one it can be both back and boost, and it can give us a wide range because of their back and boost factor or operation. It operates in 9 permissible switching states. We have 6 active states, where for these states we are talking about when one upper switch is on and 2 bottom switches are on, but none of the switches on should be on the face leg, or we can have 2 of the upper switches on and 1 of the bottom switches on, and in the same vein none should be on the same face leg. Then we can also have the 0 state, where 3 of the upper switches are all on and 3 of the lower switches are all off, or vice versa. We can also have the shoot through state, where 1 of the face leg, both the upper and lower switches are all on, or even 2 of the face leg, we have all the upper switches and lower switches all on, or even all the 3. We also then did was that we modeled the converter circuit into an equivalent circuit. We saw that in the active state, current will be flowing through the load, so the inverter bridge is seen as a current source to the load. But when it is in the 0 state, the terminals of the load are short-circuited, so no current passes through the load. In that case, we see the inverter bridge as an open circuit, just as it has been described here. And now we can let our switching sequence be such a case that for a particular time t1, we are saying we call it the non-shoot-through switching cycle. Then for a particular time T0, we are calling it the shoot-through switching cycle. In the shoot-through, what we realize that the inverter bridge is seen as a short circuit because the upper bridge and the lower bridge is on, totally boycotting the load. And we also see that the diode seen there to block reverse current is seen to be reverse biased. Our circuit analysis continued, and we came to find out that for the DC link voltage, we have this equation. We found out that we can call VC minus VL to be equal to our DC link voltage. Then we also deduce what we call the boost factor from the switching cycle, either from the switching cycle or from the switching cycle for the boost, which is shoot through, and for the non-shoot through part. And we came to find out that the boost factor can either be equal to or greater than 1. With the well-known converter equation, such as our output voltage will be equal to the modulation index multiplied by the input voltage divided by 2, we came to deduce an equation saying that our output voltage will be equal to the back boost factor multiplied by the input DC voltage divided by 2, where here our back boost factor is simply the multiplication of our boost factor and the modulation index. We also had a relation for the capacitor voltage using the shoot through switching cycle. This was our simulated circuit. We did 2 simulations, one for without shoot through and the other for with shoot through. Without shoot through, we took our input voltage to be 150 volts. We took our inductors to be 160 microhenries, and we took our capacitor to be 1000 microfarads. Since it's without shoot through, it means that our shoot through switching cycle is equal to 0, and we get a boost factor of 1. With this, we came to find out that our DC link voltage was 150, our capacitor voltage was also 150, then our output voltage peak for the phase voltage was 60 volts, and for that of the line was 103.9 volts. This is our control sequence for the switches. We can see that for each phase leg, when the upper switch is on, the lower switch is off, and it's happens for all 3 phases. To confirm our analysis, our simulation gave us exact as the calculation gave us. The simulation gave us that our input voltage is also 0. Our inductor voltage was 0, our capacitor voltage was 150, and our DC link voltage was 150. The calculations, and also our phase voltages was seen for the peaking at 60 volts. Then the line voltage peaking at 103. Then with the simulation with shoot through, we decided to maintain all values except that our shoot through factor is now 0.315. With that, we can get the boost factor to be 2.688. The capacitor voltage changed from 150 to 277, and our output AC peaked at 161. Our line also peaked at 279. This is the control sequence for the switches, and we realize that the shoot through, as illustrated by the faint blue lines, where the upper switch is on and the lower switches is also on, but for a period. Then our simulation confirmed our calculation. We had a capacitor voltage of around 275, just to confirm what we had for the calculation. Our output voltages for the phase, we had 161, and this simulation results confirm that. The line voltages was also around 279, and this diagram also confirmed that.
Having gone through all these stages of calculation and simulation results, we can then prove that the effects and the undesirable effect that we have in the V source and I source converter can be solved by Z source inverter. The Z source inverter can operate as both boost or buck converter, which is not the same in either V or I source, which can only operate as either one of it. Thank you.